Now, the first memory manager system was called or known as the fixed partitioning. Don't tell them. Just after writing onto the. It's not funny either. Okay, so it's called, number one, it's called the fixed partitioning. So the first memory management system was known as the fixed partitioning. That means, you know, we're going to divide memory into parts. So how does it work? If you're asked to describe the fixed partitioning system, very simple. You say, when the computer starts, that's at the start of a computer. This is the preparation, initialization. The memory manager will upload, the operating system will be uploaded first into memory. And we know what's the maximum location. That location, that's it. That belongs, everything from 0 to this number belongs to the operating system. And it will remain until we switch the computer off. Nobody can go near that area. Only the operating system is allowed to, you know, to modify or run that area. Right, the rest of it, the memory is divided already. We divide it into certain different sizes to accommodate different size programs. For example, we might say, right, we're gonna have few blocks of memory or a few partitions of memory. Each one of them is, say, for example, 200K. So this is a 200 kilobyte to run programs that are small enough. And here's, maybe we have 400 kilobytes, couple of maybe partitions or many partitions. And here's one that's already 1,000 kilobytes or a million. Let's say 800 kilobytes. So that's what the memory manager does right at the start. This is called fixed partitioning. It divides memory already into many different blocks of areas of memory. And it calls on this block number 1, block number 2, 3, 4, and so on. And it creates a table and writes this information in that table. For example, says, okay, block number 1. Where does it start from? Let's say at the end of the operating system ends at, for example, 10,000. Let's say 10K, 10,000 bytes. This is an address, 10,000. Okay, the operating system fitted up until this point. So from 10,000, we're going to give a space here, and it's of size 200. That means it will finish. The next one is, it will start at 10,200, right? And this one is also of size 200, so it will finish at 10,400. Are you with me, guys? Then the next one, what? 10,800, and so on. So it knows this. So, and then another 400, that's 11,200 or something like that, right? And then 800 again with it, that's 12,000. So it's already splits memory into different sizes and puts it in the table here. It says this one, partition number 1 starts at location 10,000. This is the starting address, the address of this partition. This one is at 10,400. The next one is 10,800, and so on. And also the size. We can tell immediately the size, but how big is this one? This is 200K, this is 200K, this is 400, 400, and the next one is 800. And right now, there's nobody using them. They're free. So it will mark them in the table as being free, free, free. These are just like the hotels, the rooms in a hotel. In the morning, they start a new hotel. There's nobody, no customers in there. And they have 20 rooms or 200 rooms. They write them all. How big each one is. Let's say this one has 2 beds, 2 beds, 4 beds, 4 beds, and so on, the size of the room, for example, and free, free, free. All the rooms are free, and we're sitting waiting on customers. And that's what the operating system does what the memory manager does at the start. So when we switch the computer on, first thing, the memory manager comes to memory, tells the operating system, all right, you're already uploaded, and find out what's the maximum address. The rest of it, divide it, split it into many partitions. And these partitions, they will not change until we turn the computer off. That's why they call this fixed partitioning. Fixed, that means the memory manager, of course, why does the memory manager pick 200, 200, 400? Because there's an administrator, a person, the manager who runs the IT department says, okay, I think we, 200, we're not having many programs that are less than 200. Let's change these size to 600, 600. So they keep changing it every day, or, until they find nice figures, things are working great, and they leave it at that. But so as long as the computer is running now, it's not going to change. Right, so that's initially. Now let's start running now. A program comes in to run. The program is 300 kilobytes. Here's the program coming in. Program number 1, 300K. So the moment the user say, execute this program, the operating system calls memory manager and CPU, say, memory, here's a program to run. So the memory manager say, right, I'm gonna put that program into my memory. Where? So it will go and search memory. Remember, all these blocks of memory are free, but it doesn't really have to go into memory and start running down the memory. It has a table, a small table. Just like in a hotel, when you come in and ask for a room, the receptionist doesn't go around, all the doors and see which one's free. They already have a table with all the free rooms in reception. So here, the memory manager also has a room or a table of all the partitions. So this is the partitions table. Every partition, where does it start? And how big is it? Just like in a hotel. This room number 312, that's in the 3rd floor. And it has 6 beds or 2 beds. That's how big it is. And it's free. There. So now, all we have to do, the program is 300. We have to go through this table and search for a room a partition that will fit that program. So that one is too small. 200, 200. There, this one. First one we find, it's 400. Say, good. Is it free or is it being used? It looks at it and say free. Great. That's why we will put program number 1. Now the table, there's another column. Say, right, program number 1 goes in there, and instead of F, we call this busy, and we don't put the program here. So the program, even though this partition is 400, but this program is only 300. So it only uses this far, this much of the memory. The rest of the memory is left unused, but it's given to this program. It's like you go to a hotel, you get a room, there are 3 of you, you say, oh, we have a room with 4 beds. Okay, you take it. But in the middle of the night, someone else comes looking for a room, they don't give them that bed. That bed belongs to this group, even though they're not using it, you're not using it, but it's still in your room. So same as this part of memory. This block from 10400 to 10800, that's 400 bytes, is given to this program, that's only 300 bytes. This program is only 300 bytes. And therefore it has extra space. Do we know what we call that extra space? First, that's wasted space. That program is not going to use it. It doesn't need to use it, but we cannot allocate it to another program. We call that fragmentation. And more important, because we'll meet another type of fragmentation, we call this internal fragmentation. Why do we call it internal? Because we allocated it to you, and you don't need it. And we cannot allow someone else to use it. So they call this internal fragmentation. So if you're asked, how does internal fragmentation happen? It happens to a program if a program is allocated more memory than it needs. A program needs 250. When we put it in a block that's 270, that means there's 20K wasted space. That's not good, right? It's not good to have wasted space. Internal fragmentation is a disadvantage. If I say to you, what's wrong? What's the disadvantage of fixed partitioning the way they used to run it? This system is no longer wrong. I need you to understand how it works. So to see how does the next system work. So it suffers from a problem. It's called internal fragmentation. And you need to know how does internal fragmentation happen. Right, another program comes in. It needs 170 kilobyte. Where do you think we'll place this program? Here's memory. A request comes in for a program that's 170 kilobyte. Where would we place that program? Where would Memory Manager place that program? Partition 1. Why? There. It starts, of course it doesn't go into memory. It looks into the table. We have a program that's 150K. We go through the partitions. This is the first partition. It's 200K. It will fit it. But is it free? Yes, it is. Well, then put it there. So program number 2 is placed in there. And now we mark it as busy. And so on. Right. A program will finish later on, so we can mark it free. Right. Another program comes in, and also, for example, any program comes in, we just go through the list. Let's say another program comes in, 190, 180. So obviously we put it in partition number 2, right? So this is program number 3 goes in here. And now it's busy. Another program comes in that needs 60 kilo, very small program. Where would we place that? Where would Memory Manager place this new program? Remember, program number 2 is here, I think, right? And program number 3 is there, executing. They're busy now, these are, and that's program number 1. Program number 4 comes in, needs 80 kilo, only 60 kilobyte. Where will we place it? Come on, guys. Who is with me? Okay, so we go through the table, we look for any partition that will fit this program. This program needs 60K. Hey, the first one is 200K, it will fit here. Right, it's busy. That partition is busy. Go to the next one, it's also busy. Next one is busy. Next one is 400K, and it's free. Great. Let's put that program here. So this program number 4, only needs 60K. We put it in this location that can accommodate 400K. What a big waste of wasted space of memory. And the next program, and of course we mark it as being busy. The next program, let's say 200K program comes in. Program number 5 comes in of 200K. Where we place it, the only block that's available left is the last one. So we put program 5 in there, and they're all executing now. So program number 5 is there, even though it's only 200K, but we gave it a space of 800K. There's a lot of inefficiency there in using memory. Okay. Any program that finishes. So I just explained to you what happens. What does Memory Manager do at the start when the computer is switched on? So it just breaks memory into different size partitions, create the table, and ready to start using. The second process is what happens when a program comes in for execution. We search through the table, we note the size of the program, how much memory it needs. We go through the table, we find the first available block that fits it. And now what happens when a program finishes? It has to be deallocated. Remember when we said the Memory Manager has a responsibility allocate memory? That's what we mean by allocate. You come in with a request, we go and search for a table, and we put the program in the correct place. That's called allocation. We give memory to a program. Now deallocate. What do we have to do to deallocate? Let's say program number 1 finishes. There, program number 1 is finished. There, program number 1. All we have to go to the room here, to the table, and change the busy into free. We don't have to go into memory and start clearing, wiping off the code of that program. Any other program that comes in, it will overwrite it and disappear. So deallocation is very simple. Allocation is reasonable enough, simple enough, depending on how long the table is. But this is really not very efficient system. It's easy, it's simple to implement. That's one of its advantages. But the disadvantage, what's the disadvantage of this system? It suffers from internal fragmentation. So they tried to improve that, and they generated a system that said this fixed partition is no good. What's better is dynamic partitioning. So dynamic partitioning is another system, the next development that happened. It works like this. I'll make it brief this time. At the start, anytime you're asked to describe one of those systems, you need to always say at the start, right? At the beginning, when the computer is switched on, we have to initialize memory. So what does the dynamic? The static or the fixed, it actually splits memory into variable different size partitions. But no, the dynamic partitioning is right. First it allocates some area to the operating system, and out of that area, the rest of all memory is kept in one big block. So this one does not partition, does not divide memory at the start. So at the start, tries to keep all memory in one big, huge block. Whatever size you have, that's the biggest program you can run. If the program is bigger than this, then you cannot execute it. Remember, a program needs to be uploaded into memory. Now, a program comes in and says, I need 158 kilobyte, 158. So this program needs 158 kilobyte. Program number 1. So we go straight. For example, all this memory starts at location 2000 or 10,000. Then we say, we give it exactly 158. We don't give it any more memory. So there's no, just notice here, there is no internal fragmentation. We know more. This is the efficient part of this. We give it exactly 158 kilobyte. So this must end at, say, 20,158. That's exactly where it ends. Now, but it creates a table and starts keeping this information. Process number 1, its size is 128, and it starts at this location 2000. So it starts at location 2000. And this now becomes a partition, and now it's busy. This partition is busy. The rest of it is all free. So it has a table as well. So remember, memory managers always keep tables in order to be able to manage and know. Remember, one of its responsibility is to monitor every part of memory. Now it knows this part of memory is busy, the rest of it is free. So another program comes in, says, I need 501K. So right, we give you exactly 501K. So we know process number 2 is 501K, and wherever it starts at this address, 2158. Where does it end? You have to take the starting address plus the size, and that will tell you exactly where it ends, okay, where every block is. So if you start at location 300 and you need 50, then you end at 350. Right, and this is busy as well, and so on. So sometimes, let's say, here's this one. I need 78K. So we give it 78K, process number 3. It's 73K, and it's busy, and so on. So another one, 403K. So process number 4, 403K, it starts certain other. Now, at the beginning, it's the most efficient system. We only give exactly as much memory as needs. We can fit so many programs. There's no internal fragmentation. Now, imagine this program, process number 2 is finished. So what do? We go to this table here and we mark it as free. Process number, partition number 2 is now free. We don't have to change anything. Now, and maybe the last process, maybe? No, let's say there's another process that was running before we finish this, say 200. another process number 5. So we had 5 processes running. This is 200K. And it's busy as well. Now this one has finished. And let's say also process number 4 is finished. So those 403 is free as well. So now we have few blocks that are free, few blocks that are busy. Now let's get a request. Let's say another request came in. Process number 6 came in and it says, I need 500K, 500 kilo. Where are we gonna give it? So we go through the table, we search for a block. Imagine we gave all these, there's no more big block free at the end. The whole memory is full. So we go through the existing blocks and find one that will accommodate it. 501 there, that one will accommodate. We need 500 or 490, but let's say 500. But it has to be free. Is it free? Yes, it is. Great. Then that's where we're going to put now process number 6. So process number 6, remember, in this system, we give every process as much as it needs. So this one needs 500, but we have a free space of 501, tough luck. So we cut here off 500K and we give it to this process number 6. So process number 6, we placed it here, but there's a bit of free space here, 1K. It's useless, it's too small, and that's really the definition of fragmentation. What's a fragmentation? It's a piece of memory that's small enough, it's not really usable. 1K is not good for any program. But this space, now it doesn't belong to anybody, because process number 5, or it's number 6 now, we gave it this block, but we only 500K of it. We only gave it 500. We gave it exactly as much as it needs. And therefore, in main memory, really, we left 1K, that's free. We should actually have it here as a new free block that's available, and it's free, but it's only 1K. It's sitting there, it's useless. So, with more and more operations, there'll be a lot of fragments. But anytime a process finishes, let's say this process now finishes. Process number 3 finishes. For some reason, let's say that 1K is not there. Just imagine. The one before it is busy, now this one is busy, and this one is free, and this one is busy. So this block is free, guys, and the block before it is busy, and this program finished. Process number 3 finished. So what we're going to do, we're going to mark this block as being free. This is how the dynamic partitioning works. It goes and marks it free. And then after it marks it being free, it looks at the block before it and the block below it. Are they immediately in memory? Immediately before me and immediately after me? If they are, let's join together, because we're both free. So in this case, this block is free and this block is free. That's wherever they are. That one and that one are free. This one is 78 kilobyte and this one is 403. Just let's make numbers easy. Imagine this is 100 and that's 400. They're both free. So instead of having 2 blocks, one is 100, one is 500, immediately one after the other, let's just join them into one. So the size is going to be, instead of 100 and 400, is going to be 500. It's like you and your neighbor, or let's imagine your neighbor is your friend or your brother. You decide to share things together. So you have 2 areas, one next to the other, join them into one area. So the total area is going to be the sum of those. So imagine this is 100 and that's 400. We join them, we're going to have one block of 500. Where does it start? Does it start at this point or the second point? It starts at the top one. So now we have a free block and it's bigger and it starts at wherever the first block starts. Now, this is what the dynamic partitioning does. Every time a program finishes and a block becomes free, it checks the block before it and the block after it. If both of them are free, it will merge the three of them together. And the total block, imagine if you had 3 blocks, each one of them is 100, 100, 100. If you merge them, the 3 of them, we're going to have one big block of size 300. And where does it start? It starts at the starting point of the first one. And that's what it does. So it comes into this table, and instead of having 2 blocks, we'll say, hey, we only have 1 block, and the size of it is the size of those 2 together, and that's the starting point. And every time another program finishes, it will try and merge with the one before it or the one after it, or with both of them. And if most of them finish, we're going to start having bigger blocks again, that we can accommodate bigger programs later. And that's why they call this the dynamic partitioning. You partition, but when they finish, join them together again, try and have a big block. But it doesn't always work. The more you run program, start, program, finish, when you come down looking for a program that, for example, you have 500K that's became free. Now you get a program that wants 490, you end up giving it out of this one, you have another small fragment of 10K. And after a few hours of operation, you might have hundreds of fragments. You might have, and what's a fragment in the dynamic? It's a small space of memory that's free, available, but it's too small. But if you have loads of these fragments, you might have big amount of memory that's free, but it's useless. Let's say you might have 2,000 bytes of memory, let's say, but they're all 100 bytes each in different areas. So if a program comes in that only needs 1,000 bytes, and you can, like memory manager, will probably keep a total of all the memory used and total of all the free memory, says, I have a lot of free memory, but I can't find a block that's big enough for this one. Why? Because you have a lot of fragments. And they're called external fragments. External fragmentation is slightly different to the previous system where we had internal fragmentation. Remember the difference between them. And you will probably be asked the difference. It was asked in exams before. What's the difference between internal fragmentation and external fragmentation? And internal fragmentation happens when you give a program more memory than it needs. You allocate memory to that program, it doesn't need it. Like this program needs 100, I only have a block of 200. You take it. So you only use 100, the rest of it is all internal fragmentation because we can't give another program that space. We call that internal fragmentation. But external fragmentation usually happens if you have a block, let's say a block of 100, and a program needs 90. So we go to that block 100, we break off 90, we say, there you are, that's exactly how much you need. But that's, you left us with 10K, which is very small space, and we call that external fragmentation. So you need to be able to explain how does internal fragmentation happen, or how does external fragmentation happen. Okay, so that's dynamic partitioning, and that solved the internal fragmentation. If there is no internal fragmentation in this system, so there's no space wasted. Why? Because we give every program exactly as much memory as it needs. There's no such thing as internal fragmentation now. But this one suffers from external fragmentation. The previous system did not suffer from external fragmentation. But this problem really, this system did not work very well. So they modified it. It's the last system I'll talk about today, and the simplest as well. And they called it the relocatable. What time are we at now? See, we stop, most people don't return. What time is it now? 3? What time? Okay, let's just stop for a second, pause for a second before we talk about the next system. What time are we supposed to finish at and then come back again? Anybody knows that has the timetable? We started at 1:30. What time are we supposed to finish at? 3:30 or 4? 1 at a time. We started at 1:30. We don't finish at 2:30. 3:30. Okay, so up to 3:30. Oh. Okay, and then we come back again at what time? 4, and we finish at 5:30. Right. So that's an hour. So how about if we continue until today, until 4, we see how it goes, and then that's it. You go there. Is that okay with you? So you put up for, but you save yourself. Okay, and we see how it goes this week. If it doesn't work, we'll change it next week. Yeah, you have a question? Somebody put their hand up there. Okay. You were objecting to this suggestion? Okay. So, what's wrong with this system, the dynamic partitioning system? What's the disadvantage of the dynamic partitioning system? Let's just revise, just to make sure you're actually with me, guys. Any idea? External fragmentation. External fragmentation. That's the problem with the dynamic partitioning. How do we get external fragmentation? Right? See how today you barely say think about it. In 3 weeks, I'll ask you, so that's what I want. But eventually, but okay. So, yeah, do you want to rephrase it better? Yeah, correct. External fragmentation. Yeah. So when we allocate from space to a program and we have the tools on use space, that can be used. Normally, we allocate every program memory from a block. Maybe the best way is to give an example. You say, right, if we have a block of 100 and a program needs 98. So we chop 98, give it to the program, and the program always gets what it needs exactly in the dynamic partition. What's left is too small to be useful, and we call that external fragmentation. Okay? How about internal fragmentation? How does internal fragmentation happen in the previous system, the fixed partitioning?
When a program is allocated with more memory than it needs. Like memory that is
perfect. You don't have to say anything. You put that answer in the exam, you get the full mark. Fixed, no, sorry, not fixed partition. Internal fragmentation. How does it happen? Yeah, you can use an example as well. If a program needs 100 kilobytes, but we only have a block of 500 kilobytes. If you give it to that one, the rest of that memory that's given to the program that does not need is considered internal fragmentation. And the small definition, how it happens, is given a program or allocated to a program or a process more memory than it needs. That's a perfect definition. All right. Hey guys, let's say just another point just to bring across. And the program needs 200K. And this is what we have, the 3 blocks that we have at the moment. We have a block that's 300K, 3. And we also have a 200K, 3. And we have 800K, 3. So we have 3 blocks in memory, wherever they are. They could, but they're in this order. Maybe in between them there are a few blocks that are not free, but that's how they are. There may be dozens of blocks between that one and that one that are busy, but this is the next free one. And then there are a few more busy blocks, and then there's this one. Now a block comes in that needs, what did I say, 200. Where would we allocate it? Now this is dynamic partitioning. Right? So we're going to chop off part of a block and allocate it to it. So what do you think? Where are we going to allocate this one? But we're going to give it or place it here, even if it was the fixed partitioning. Let's talk about fixed partitioning for a second, it's easier. But we're going to put the program here or there or there. Pardon?
Maybe
the top one. So if this is the way it actually, the method works, it says, go through your table, find a block that will accommodate this program, and make sure it's free. If it's free, then allocate it. And so, and this is called the first fit method. So there's a method called first fit. Go through the table, the first one you find that fits, stop there, allocate the process there. So you go and put that program there, 200, you put it there, and you mark this as busy. And that's it, and the program started working. Of course, if it was in the fixed partitioning, there'd be a lot of internal fragmentation waste. Ideally, we should give it as much as it needs, or pick the smallest process or program that we need. Now, the next process is called the best fit. So there's another way of allocation. Are we going to use the first fit or the best fit? It's up to the administrator. It's up to you to tell the memory manager, go for the best fit, or go for the first fit. Now you know how the first fit works. Well, if we go for the best fit, which one do you think, which partition do you think we will be allocating this program? Partition 1, 2, or 3? 3, because it fits it best. So how would you describe, how do you tell somebody who does that job, with instructions, what would you tell them? You go through the table, compare each one of this to the size, right? That's 300 and that's 200. There's a difference, maybe about 100. You keep going down, and that's a even bigger difference. Notice the smallest difference until you finish the entire table. When you finish the entire table, then you have already now decided which one is the best fit, which one is the smallest outfitted. It may not be 200, it could be 210, but that's the most suitable one. You allocated that one. So this is called the best fit. So see, when you have the logic, you can describe it on your own. In the exam, the question says, describe the first fit. You say, right, when a request comes in, we go through the table. The first one we find that fits it, that's free, we use it. Describe the best fit. So when the request comes, we search the entire table. And by going through the entire table, we find out the one that's nearest to that program. And don't use the word best fit. Many times, if you are asked a question, by the way, to describe anything, let's say in this example, best fit. Don't say we go through the entire table and the one that best fit we'll use. No, then you did not describe. You don't get, I know what you mean, but don't use the same words that you're asked to describe or explain. Right, but that's how it works. You say, you go through the entire table, notice, which of those that is the smallest block that can fit this. You can only know if you go through the entire table. And if it's free, then we allocate that. That's called the best fit. As you notice, maybe the best fit might end up giving us a lot of fragments. Imagine if the request that comes in is, let's say, 390. And we say use the best fit. Where would be the best one to fit 290, sorry? If our program needs 290K, which one of these will be the best fit? The top one. But if we chop 290 out of this one, that will leave us with fragments. So the best fit always tends to leave you with lots of fragments because you're always going to look for the smallest one that fits. And the smallest one that fits will give you only a tiny little space, and you end up with having lots of external fragmentation. So somebody came up with another idea, say, how about go for the worst fit? So that's another technique called the worst fit. Can you tell me what the worst fit is? You've never heard it before, but now out of the opposite of the best fit. How would you describe the worst fit?
You need to allocate the program to a block that has more
You go through the entire list of the table and find the one that has the biggest block, and that's the one we'll allocate from. Is that a good idea? It tends to be, because remember, this is 800. If we have 290, that will leave us a fragment here. That's unusable. But if we allocate it from here, it will not leave us a fragment, still leave a big block, and that 300 is still there to accommodate something that. So that's called worst fit. So you need to remember those techniques. One is called the best fit, the first fit, and the worst fit. Which one is better? Which one is the best? Any idea? Which of those techniques is the best? First fit, best fit, or worst fit? Worst fit is a good answer. That is not the right answer. What do you think? What? Not the right answer. Right. Anybody has any preference? But you need to have a reason. Like, the good thing is, don't say this one. Anytime you're asked which one is better from now on, A or B. Never say A or B. Say A has this advantage, or A has this problem, or in this case, A might be better in this case. So you have to give some reason why you think A might be better than B, or B might be better than A. Yeah. Okay, yeah, the worst fit will always leave big parts. Well, what's wrong with the best fit? What's wrong with the best fit? Any idea? It will leave a lot of small fragments. Each time it allocates, trying to find the smallest block to allocate from. And that will give even smaller fragmentation. It has another problem. The first fit is not really the best, but it has an advantage. Anybody knows what's the advantage of the first fit over those two? You don't have to search the full table. Because searching the full table can delay the allocation process. It's like you want to buy something, you go there and there's a list of 2,000 items to go through. You have to be searching until you find the one that suits you, out of a long list.
But if we use the worst fit, we just get a single partition.
Yeah, but no, after a little while, when they start finishing, you're going to have lots of partitions. You have to search. The table grows longer and longer. There's one last fit, guys. Guys, the first fit is the easiest, is the quickest to allocate most of the time, not all the time. By easy talking at. You have a table, you keep going until you find one that fits, and there it is. The other two, the worst and the best, you have to search the full table and keep in mind which one was the best. Every time you find another one, you keep in memory where is the next best one. But the problem, so first fit is good, but the problem with it, that every time you start from the top of the list, you're going to have fragments at the top of the list. You might have 2,000 fragments at the top of the list, and there are 6 huge blocks down at the bottom, but you never go near them because you always start at the top. So they introduced another one. Don't always start at the top. Start at the top when you find, let's say you're looking for something like 500. You go down, this one is good. This is first fit. We stop here. We chop 500, but leave the link there, leave the pointer there. The next request, we don't go start at the top of the list. We start from wherever we started from. So we keep going down and we stop there until the next request. And then when you reach the end of the list, you go recycle and go. So you're always recycling the list, but you don't always start at the top of the list. And that way you spread the fragmentation or spread the distribution. You get better distribution in the list. But that's called the next fit. It's known as the next fit. So they tried those. Probably they didn't try the worst fit before they changed the entire system, but you need to know the differences or how they work. Or if I give you an example like this, and I say, which block would you allocate this if we were using the worst fit, the best fit, the next fit? And you should be able to say, oh, the best fit. I mean, you know, I have to search that one would be the best fit. This one would be the worst fit, or first fit, or whatever. But what's the advantage and disadvantage of each? Now, what's the problem with the best fit and the worst fit? The best fit? Yeah, the best fit will generate even smaller fragments. Any other problem with it?
You need to go through 18 minutes.
Yeah, the whole list needs to be searched, and that delays makes the allocation a little bit slower. All right, the problem with this system, the dynamic system, is the fragmentation. The longer it runs, the more fragmentation there. We know every time we do a deallocation, if you're asked what's involved in the deallocation in the dynamic memory, what do we do for deallocation? So in dynamic memory, if a program becomes free, if a block becomes free, what do we do? What are the steps involved when a program finishes? Did you do that course before, this course before? Okay. Right, well, you're ruining my surprises. So we use you as a reference, right? Somebody says, give us the wrong answer, I refer to you.
So you go to the table and then change it, and just look at if they ask if it's free, you change it. If it's busy, you change it.
Yeah, I think so. Can you tell me the steps involved? I didn't quite get it from you. Right, you know what the steps involved when a process finishes here? We call it the deallocation. What does the memory manager do to deallocate that space? Let's say this process was running, this space was allocated to it, now it's finished. We need to do a deallocation. What's involved in the dynamic partitioning during deallocation? Pardon? Just mark this as free.
Yeah.
That's in the first fixed partitioning, but in the dynamic partition, there's another step involved, as well as marking it as free.
You look at the block above and below and merge the.
You try and merge that free block, check the one before it and the one after it. If both of them free, or one of them is free, merge the free ones. If the two are free, then merge the three of them together into one bigger block. So that's how the dynamic is trying to always get rid of fragments, but it doesn't always work. And therefore, they came up with another system, and it's called the relocatable. This is system number 3. So this is the third memory system we look at. Relocatable dynamic memory management system. So how does the relocatable dynamic memory management system? First, it's dynamic. So at the start, is how you describe it. Anytime you describe a system, you tell us a statement or two. What happens at the beginning, at the start, when we switch the computer on, and then what happens when a process comes in, a request for memory comes in, and then what happens when the process finishes. So you need to understand those 3 steps in every memory manager. At the beginning, does it break memory into fixed partitions, or does it keep memory in one big block? So the dynamic tries to keep it in one big block at the start. So I'll explain this. The relocatable dynamic, just like a dynamic. Don't forget the first part, that memory, the operating system has allocated its own space in memory. The dynamic keeps the rest of memory in one big block. Well, that's all I have to say, but at least you show you understand the system. We want always to have one big block if we can. Of course, it doesn't always happen. And now the next step, when a program comes in, a request for memory, we give each program more than it needs, or exactly as much as it needs in the dynamic. Exactly as it needs. So if this one needs 550, we give it exactly 550. And we need, in the table, we know the size, the address, and which program is there, which process is there, and whether it's busy or free. In fact, the dynamic partitioning keeps two tables, one just for the free blocks and one for the busy blocks, but it doesn't matter for now. So, and that's it. Every time there's a request, we allocate that let's say this is 200K, this is 750, and so on. Initially, dynamic partitioning system is so efficient. But after a little while, as processes start finishing and another process comes in and we have a block of 750, but another process that needs only 720, we've chopped that out of it, then that leaves us with fragments. Fragments start forming. Some of them get merged eventually, but we end up with lots of fragments. That's the problem with dynamic partitioning. There's fragment, I'll just mark it here as F, well, not free, but fragmentation. There's a lot of wasted external fragmentation. Remember, it's not internal fragmentation, right? Or is it? Okay. So we have a lot of external fragmentation. So this is the new system now, the relocatable. They said, let's have a function, and we call it compaction. What does the word compaction mean? It means rearrange things in a better way. Like when you want to travel, you have a lot of stuff, but then maybe your younger brother or sister say, leave it to me, and they actually only half the suitcase now is fitted everything, because they compacted everything so neatly and nicely. Same here, the function of compaction is actually trying to get all these free fragments together and all the blocks packed together, the busy blocks. So what compaction does, it moves all the busy blocks to one end of memory and all the free blocks to one end of memory. And when it has the free blocks, it joins them together into one big block. Okay? So all these little free fragments that are there, you put them all there in the bottom of memory, and they're all free, it joins them all in one big block. So it's a way of claiming back the lost fragments of memory. That's what the relocatable, that's why they call this relocatable. That means every now and again, you call the compaction function. The compaction will relocate all these programs. It will move them in memory. If this was, for example, was here at location 10,000, no, we're going to move it up to location 2,000. There's a function in operating systems, in Unix and in Windows, and it's called defrag. But that's for hard disk, for files. You know, as files are put on a hard disk, they're broken into smaller units and put everywhere, and eventually it becomes like this one, you know, badly managed. So there is a function, you can actually run it on your machine. It's called defrag. It's part of the operating system, but it's not part of the kernel. It's not happening all the time, only you might run it once a year or so. So you can call it and run it in Windows and Linux. It's called defrag. And what defrag comes and fixes your hard disk, moves all the files, puts them, stack them up, and shows you now there's bigger usable space of your hard disk. But this is on main memory. Now we're talking about main memory here. So compaction is like, I just said it's similar to defrag on hard disk, but it claims back the function of compaction. Compaction is a function that will claim back external fragmentation and join it all into one big block, free block. And it does it by actually moving all the busy blocks to an end and all the free blocks to an end and merge all the free blocks. Of course, yeah?
How it moves the blocks?
You actually stop executing when the file manager calls the compaction. This is not something that a user would call. On the hard disk, yeah, a user can do it to their hard disk, but on memory, no, this is part of the, the file manager. The file manager will say, right, we're going to run compaction. So compaction stops execution and says, okay, look at this memory, says, let's say this guy here, 500, busy, and this is free, right? So I'd say, move this one from here up to this point. So this program that's busy, it's moved up, so it leaves the free space down there. And now there's more space there. Now there's another program. So you might say, okay, that's 40K. We have a program here called 40K, or, you know, let's move it in there. Now it will fit in there. So to keep moving, all the programs are packed one out on top of the other. And down at the bottom, you are left with lots of little free fragments. So I'll start joining them 2 at a time or 3 at a time, merge them all together into one big free block. And then you can continue on working again, and maybe a few hours later, you might start having again more fragments. Now, how does the memory manager, okay, everybody knows the general idea in compaction, in the relocatable. The word relocatable, that means you relocate all the programs, move them up, stack them, and pack them nicely into one end of memory, into the higher part of memory, and leave the lower part of memory for free fragments and blocks. And that's then, when you join them together, you have big free block. Now, when this is a slow operation, execution stops, and you have to wait for a few seconds. When we say a few seconds, like a CPU is doing something else. So no processes, nothing is running really. These programs are not executing anymore. We are being moved. It has 2 little issues, well, 2 big issues. One of them is the time wasted. So it's a slow operation. If you do the defrag on your computer, it'll probably take 3 or 4 hours to move things and pack them up again. Sometimes you might even have to run it overnight, hopefully, but it's good. Your hard disk will work a little bit faster after a defrag. Here with memory, we'll definitely have more memory. So that's one of the first problems, that's slow. It slows execution completely, so it's not really a great thing to be running all the time. Now, when do you think file manager will say, okay, let me run compaction? I need to run compaction. Any idea? How would the file manager, when do you think the compaction process is run?
You're out of memory?
How do you know you're out of memory? You're not really out of memory.
You have a new program that doesn't have enough memory. You put in a block. So
you don't have enough memory to serve a request. Yeah. Let's say a program comes in and say I need 400K. You know the total amount of programs that are running, for example, in your memory, and you know the total free space in your memory accordingly. For example, I know I have 800 kilobytes of memory free, and a program comes in that only needs 300 kilobytes, and yet I cannot accommodate it. Why? Because I have lots of fragments. I have 800K, but they're all in small chunks, small 10 and 20Ks and all that. But I don't have them all together. Then I know I have a problem of external fragmentation. And I know that's a good time to let me run the compaction. Compaction, you don't want to run, just for, to improve performance, because it's a really bad performance itself. You don't want to run it unless you actually need it. So and that's one time when you decide you need it. Some systems, they say, let's run it. And we know at our busiest time, say maybe 2:30 or between 2 and 4 o'clock p.m., we have so many programs run, and the system's been running since the morning. It has a lot of fragments. Let's run it at 3 o'clock. And they decide a particular time to run it. And it solves their problem for that time. But that would be, maybe keeping an eye on requests that come in that you cannot afford and they're sitting waiting. If you get 2 or 3 requests that you should be able to afford to run them because you have a lot of memory, but the fact that you cannot run them because your memory is fragmented. So maybe that would be a good time to run the compaction operation. The other problem, and this is the last thing we'll talk about today, the other problem of the compaction. Remember, every time you put a program in memory, let's say you've written a program. And execution in programs is not always sequential. It starts sequential for a few steps, and then suddenly you might jump to line 500 in your program, or line 800, because you have a function there or a process or whatever it is. So, when you say jump to line 300, where does it start from? Where's your reference in a program? Your reference is the first line, being line 0 or line 1. Location 0 is there. So if we say line 700 in your program, that means 700 from the top of your program, from the starting point. Now, when you put this program into memory, I say this is memory, and the CPU is there executing your program. Your program is here in this part of memory. And then when you say go to 700, line 700, that's the address 700. In fact, 700 is there somewhere up in memory. So remember, every address is implemented. In your code, if you say go to function, whatever it is, function that will sort the numbers, it's here. It's translated immediately. That function is on line 500. 500 starting at this point, so it jumps to location 500 and start executing. But when you have that program in memory, if you say go to location 500, that's not in your program, it's up there somewhere. So these addresses in memory, when you have code and that code is translated into, it's by the compiler, the compiler uses that addressing as being 0. Every address in your program is treated based on the point that the first location of your program is 0. But now when you put this program into execution, the memory manager will put that memory with the program. It knows it. For example, you put the program at location 2000. But how does it know, when you say go to location 500? Now the memory manager and the CPU, well, not the CPU, but the memory manager, every reference that's made in your program, it adds to it your present location. So when you say 500, we don't change that. The compiler say go to line 500, but we always add to it location 2000. So now every reference your program makes, we add to it your present location in memory. That's how they solve this problem. Otherwise, you as a programmer, you need to always know exactly, say, where are you going to put my program in memory? It's location 10,000, but then let me change the addresses. No, these addresses are calculated on your behalf. You don't have to worry about it. As long as the first reference is always number 0, you just work with that. And if we put your program in location 2000, we'll add 2000 to every address in your program. If we put it in location 2000, we'll keep adding 10,000. But we never change. Like once the program is put in this part of memory, so every instruction, if you say change X, where's X in your program? It's on location 700, but now it's 2700, which is still there within your limits. Let's say here 3000 outside your area. So every address generated by your program, we add to it the address. Now comes the problem of relocation, compaction. Compaction comes and moves you up 1000 bytes. Now it ruined all your addressing system. So now we have another register with another address that's called the relocatable address. In fact, they have a register called the relocatable register. It always has the value 0. And it's always added to your address. So if you say change something in location 300, we add to it your present location 2300, and we add to it the relocatable, which is 0. So that you still end up in your correct area. But now imagine if you were moved upward in memory. So the relocatable address is going to be minus 1000. It has to be added now to every address. Like we were adding the zeros, but now we're going to add minus 1000. So now every address you make in your, let's say, change location 500 in my code. or we'll go to line number 500. So now we add to it 2,500 minus 1,000. That means it's going to be 1,500 because your program was moved up to that location, 1,000. So relocation or compaction causes a problem with addressing, but they solved it by adding another number. If you are moved upward, we give you minus shift that happened to you. And we always, every address from now on you need, we'll always add to it minus 1,000 or 2,000. And if you move downward, then it's going to be a positive number. Okay, and that's called the relocatable address, and it's kept in the register. A register called the relocatable register that's always added to every address. When you are loaded first time, it has the value 0. It's still added to your address, but doesn't make any difference. So that's another problem with relocatable addressing caused by the compact function. That's it. So these are 3 memory addresses we look at, memory management systems: the fixed, the dynamic, and the relocatable dynamic. None of them is used at the moment, but you needed to know that background. But the next one we're going to be looking at next week is called the paged memory system. That's what's in use today. The paged, where they found it's neither good to break your memory at the start into different partitions, and it's not good either to use the dynamic partitioning. It's best to split your memory into equal size spaces, blocks, small blocks, and they're called pages. And a page is always usable. It's not too small to be useless, but we'll see later on how we can break every program as well in pages, and we can put pages in different locations. But we'll worry about it next week. So now I just need you to understand those, and I need you to look at them. And I'm going to ask you a few questions now before you go home. How much time have we got left? 15 minutes. Yeah, okay, plenty of time. Now, well, I won't keep you for 15 minutes, but let's. Okay. Fixed partitioning system. Who would give me one statement describing the fixed partitioning system? The simplest, the first system we started with. How would you describe it?
Main memory is initially divided into fixed partitions.
Exactly. So at the start, when a computer switched on, memory is divided into variable size blocks of memory or partitions. Okay. Now, what happens when a program comes in for requesting memory? A new program.
No cases, it depends. In all cases, the first partition will fit in.
Yeah. So it searches through the partitions that are available, whichever one that's available, that can accommodate it, and that's free, depending on a particular policy that we'll be considering later, then it will be allocated to it. And what happens when deallocating in the fixed partition? What needs to be done? Any idea? A program is executing in the fixed partitioning, the old fixed partitioning system.
He changes to 3, that's it. And then if another program goes into it, it'll override over.
Yeah. So all you need to do in the fixed partitioning system, you don't even need to go into main memory, into the main part of memory. You go to your table and you see, which this is like hotels, customers in a hotel. At the reception, you have a table. Customer leaves, all you have to go there, which room number, you go and mark it as being free. And that's all. Maybe in a hotel, they might send the cleaning staff to go up there and tidy it up for the next customer, but here we don't need to do that. Okay, what's the disadvantage of the fixed partitioning system? The idea? Did you say external fragmentation? Internal fragmentation? What's the disadvantage? What's the problem with that? Is it internal or external fragmentation? Internal, are you sure?
Yeah.
How does internal happen? Here's a program, here's a block that's 400 kilobytes. How do you get internal fragmentation? So if we allocate this block that's 400, if we allocate it to a process that needs 500, is there fragmentation? Or we cannot allocate it to a process that's 500. What if we allocate a 400 block to a process that only needs 300 block? Then we have the internal fragmentation of 100K. Okay, so internal fragmentation, anybody knows how does it happen? How does internal fragmentation happen? Somebody gave us a beautiful definition. How do we get internal fragmentation? Yeah, I think so. If we allocate a program more memory than it needs, then all that extra memory allocated to it is considered internal fragmentation. Right, and how does external fragmentation happen?
It occurs when total unused memory space is enough to answer all the allocation requests.
I think you probably answered how, when do we need compaction? No, I'm going to restart. Maybe I misread you. How does external fragmentation happen? Okay, external fragmentation, how does it happen? Anybody?
It's when a block is allocated, like it's when little space is left between allocation of a program. So if a program needs 190K, when the 10K left over is
yeah, maybe it's always easy to give an example. You know, you have a 500 block and a program that comes in says I need 490, 495. We break 495, you're left with 5K. It's too small to be useful. That's external fragmentation, and not allocated to anyone. That's called external fragmentation. What's the problem? Well, describe the best fit allocation policy.
Solve for the entire table.
Yeah?
And then select the nearest difference.
Exactly. So you search the entire table and you look for the block with the smallest difference and you allocate from that block. What's the problem with that, with best fit?
The best fit is slow.
Slow at allocation. Yeah. Okay. And sometimes it leaves smaller fragments. Right. What's the advantage of first fit? Okay, thank you. Went a long way about it, but yeah. Okay, so first fit, you allocate from the first available block that you see. You don't have to search the full list, and therefore allocation is a little quicker than the best and worst fits. But it leaves a lot of fragments at the start of the list, so next fit is the better one that allows distribution. Right, okay, what else did we talk about today? We didn't talk much today. When would a memory manager decide, I'm going to terminate this process? Why do you think they might terminate it? That's okay, thank you. That's normal termination. That the program finished its last process and it finished. Give me another reason why memory manager might decide to terminate. It decides, not the program decided. The memory manager decides this program has to be terminated.
If the program tries to access memory that is not its own.
Exactly. If a program tries to access memory, it doesn't belong to it, then it will be terminated. When do you think, what's the advantage? Give me one advantage or a disadvantage, or one of each, of compaction function. Give him an elbow, please. No, an elbow. Okay. Compaction function, what is it? Well, yeah, now that we have you, what is it first before you answer that question? Compaction function. Okay, we can answer it, come back to you. Anybody here wants to tell me what the compaction function is?
It's when we move the busy blocks upwards, so we can have all the fragments and the right we can merge them.
Compaction is moving all the busy blocks to one end of memory. Sometimes they go to the other end, but they always, let's say all the busy blocks are put to one end, all the free blocks on the other end, and we merge the free blocks with the purpose of hopefully getting big space, one big free block. Now we can accommodate even more requests. Now what's the advantage of that, doing that? Well, I already told you what the advantage is. So what's the disadvantage? Neither. Okay, next person, yeah. Another one. Yeah, go on. Advantage of compaction. Come on, guys, I know I said you don't have to answer, but give it a go. It doesn't matter if it's a wrong answer. Okay, so the advantage is that we will claim back all that lost fragments. What's the disadvantage?
It's a slow operation.
It's a slow process. You don't want to be doing it all the time. How much of a program needs to be uploaded into memory? We're using the fixed and the dynamic partitioning. How much of the program code needs to be in main memory? 50% of it or 80% of it? What do you think? 80 is a good answer, but it's the wrong answer. How much of a code of a program needs to be in main memory according to the fixed and dynamic and relocatable dynamic? 50%? The whole lot, 100% of the program. Did you say? Yeah, okay. I'm not sure what you said, but yeah. Remember, the requirement up to this point is that the full code, full program has to be in main memory, and it also has to be in one continuous block. We can't have part of it in one block and another part in another block, not at that point of time. Then it's only in the 90s, when we started going for paging. The year 2000, we went for virtual memory. So next week we'll do those two, and this is what we have today. Right, okay, what else? I'm sure there's more questions in there. What's the advantage of fixed partitioning? If you get a question, okay, describe fixed partitioning, and give me an advantage. What's the advantage of fixed partitioning when compared with dynamic partitioning? Any idea?
Partitioning is.
Hold on, I have volunteers here. Yeah? No? Yeah?
Fixed partitioning is a lot more straightforward than dynamic.
It's a lot easier to implement. It's less complicated. What about its disadvantage? What's the disadvantage of fixed partitioning? Internal or external? Internal fragmentation, yeah. And what's the disadvantage of dynamic partitioning? External fragmentation. Anything else? Okay, what's the disadvantage of the relocatable dynamic? Disadvantage or advantage? No, give us disadvantage. Relocatable. The relocatable partitioning is the one that moves all the different blocks, the full blocks one end, the busy ones, and the other ones the another end. We know it works, it claims back the lost fragments. That's its advantage. But what's its disadvantage? It's what? I can't hear what you're saying. Speak up. Slow process. Yeah, I think I got it. Yeah, so it's slow at the end. Jeez, I'm gonna get you microphones or me speakers, or headphones to hear. Yeah, no, I know. They work. They're good for recording here, but I'm trying. Maybe okay. Maybe it's just the age. I can't hear you. Okay. Thank you very much, guys, and I'll see you next week.